Welcome to this concept explainer brought to you by CBSE ScoreLab of ProfSam.com. That is ProfSam.com. Today, we are undertaking a really crucial deep dive into power in AC circuits, specifically the power factor. It's a key topic from Unit 7, Alternating Current, and we promise you a simple, exam-safe explanation that will clarify this concept, well, once and for all. You know, when we were studying direct current or DC circuits, calculating power was probably the easiest thing. It was simply P equals V times I. But alternating current is far trickier because the current and voltage are constantly oscillating, changing magnitude and direction, many times every second. And this oscillatory nature, it introduces a critical complication. We can call it synchronization. We absolutely must understand the power factor because it dictates how efficiently energy is actually transferred. It's the concept that explains why a huge factory might have to pay serious financial penalties just for having too much, let's say, foam in its power supply. Okay, let's start with a very simple question. An everyday scenario. Imagine your standard household supply, 230 volts.
Now, if you connect a device, maybe a large motor, and you measure that it draws a current of exactly 10 amperes, does that automatically mean the device is consuming energy equal to the full 230 volts times 10 amps, which is 2,300 watts?
Instinctively, I would say yes. I mean, power is V times I. If the voltage is there and the current is flowing, power must be consumed. I'd expect 2,300 watts.
Exactly. And that is the expectation our knowledge of DC circuits sets up for us. But here is the really surprising, sort of counterintuitive fact, which is central to this whole chapter. A device can be running, drawing a full measurable current of, say, 10 amperes, yet simultaneously consume 0 watts of actual average power.
Wait, what? That sounds impossible. How can that be? If the ammeter is showing 10 amperes, there's a huge current flowing. So the source is definitely delivering something. How can the net energy transfer be 0?
The answer lies entirely in understanding the phase angle, phi, and how that translates into the power factor. See, the core idea is that in AC, the voltage V and the current I might not be perfectly in sync. They can be out of phase. Imagine V and I are dancing partners. If they take steps together perfectly when V is maximum, I is maximum, that's perfect synchronization. But what if V peaks exactly when I is passing through 0?
Then the instantaneous power, which is V times I, would be 0 at that moment.
Precisely. And the power factor, which is defined mathematically as cos phi, is simply a measure of how perfectly those two, V and I, are synchronized. The closer cos phi is to 1, the better the synchronization. Now, to really internalize what this power factor represents, let's use a classic engineering analogy, the beer mug. You must remember this, not just for the exam, but for life. Imagine you order a large mug of a beverage. The total size of that mug, the volume the utility company must generate and the wires must carry, is called the apparent power. We use the symbol S for this, and it is calculated simply as V times I, and its unit is VA, volt amperes.
So apparent power is the total capacity the power plant has to supply, regardless of what we actually use.
Exactly. Now, inside that mug, the actual liquid at the bottom is the real power. This is the useful energy, P measured in watts. This is what actually turns the motor or heats the water. And then on top of the liquid, you have that frothy foam.
Okay.
This foam is the reactive power, Q. Its unit is VAR's volt amperes reactive. It takes up volume in the mug and it takes up space in the transmission wires, but it does absolutely no useful work for you. It's just there. So the power factor is simply the ratio of real power, the liquid beer, to the apparent power, the total mug volume. A perfect power factor of 1.0 means the mug is 100% liquid, 0 foam.
0 foam. That happens when the phase angle phi is 0.
Exactly.
I think I get the analogy of the liquid and the foam, but is that foam energy the reactive power? Is it just lost, or does it go somewhere?
That is a brilliant question. That's a critical distinction. The reactive power is not dissipated as heat the way real power is. It's the energy that continuously sloshes or oscillates back and forth between the source and the inductor or capacitor in the circuit. It's borrowed and returned every single cycle. But here's the big problem for the utility company. This is why they charge those penalties. The transmission wires, you see, they must carry the total apparent power, V times I. So if your power factor, your cos phi, is low, it means your current, I, must be dangerously high just to deliver the same useful real power, P.
Oh, I see. To get the same amount of liquid, you need a much bigger mug if it's half full of foam, so you need more current.
Precisely. To deliver 100 watts of real power with a power factor of 0.5, you need to supply twice the total current than you would if the power factor was 1.0. And this unnecessarily high current flowing through the grid causes massive, genuine I²R heat loss in the transmission lines, wasting fuel, heating the environment. For a final mental image, think of pushing a child on a swing. The power factor is your push timing score. If you push forward perfectly at the peak of the swing, so perfect timing, phi is 0, all your effort translates to motion. That's a power factor of 1.
Okay, maximum effect.
Maximum effect. But if you push too early or too late or even a bit sideways, you are spending effort, but very little of it translates to useful motion. That wasted sideways effort is your reactive power. The power factor is just how good you are at timing that push. Okay, now that we have the analogy, let's anchor this concept with the formal definitions from Answer. Could you please read the key formula for average power as it's given in the textbook?
Yes, it says, the average power over a cycle is given by P equals VI cos phi. The quantity cos phi is called the power factor. This can also be written as P equals I squared Z cos phi.
Okay, let's unpack that. The instantaneous power, PT, is the product of instantaneous voltage and current. And the expression looks complicated. It has a product of sine terms. But when we average this power over one full cycle, which is what your electricity meter at home does, the math simplifies. We find the expression has two parts. One is a constant term, and the other involves cos 2 omega t.
Right, I remember that derivation.
Yeah.
And anything with cos 2 omega t, when you average it over a full cycle, it becomes 0, isn't it?
It averages to precisely 0. That's the key. That term is the mathematical representation of the reactive power, the oscillating foam. It takes energy out and then puts it all back. Net effect is 0. So we are left only with the constant term, which gives us our final useful average power formula. P equals V arms, I arms cos phi. And please remember, in all AC power calculations, you must always use the RMS values. Now here is where it gets really interesting. We connect the phase angle, phi, to the physical components of the circuit. In a series LCR circuit, the power factor is linked directly to resistance and impedance through the impedance triangle. It is defined as the ratio of resistance to impedance. Cos phi equals R by Z.
Oh, okay. So if the power factor is just R divided by Z, why do we need to even talk about the phase angle phi? Can we just measure R and Z and be done with it?
That's a very sharp question. The reason we need phi is because the angle causes the impedance. Z is the vector sum, the result of the phase difference between the opposition from R, XL, and XC. The angle phi is the physical reason why Z is larger than R in the first place. The R by Z ratio just gives us a practical way to calculate the power factor from the components themselves. And this R by Z formula, it instantly explains the limiting cases which are so important for exams. Case 1, if the circuit is purely resistive, what happens?
Then Z is equal to R. So cos phi would be R by R, which is 1.
Correct. The phase angle phi is 0. V and I are perfectly in phase, maximum power dissipation, all beer, no foam. Now for case 2, the most crucial one, if the circuit is purely inductive or purely capacitive, meaning R is 0, what's the power factor then?
Well, if R is 0, then cos phi is 0 by Z, which is 0.
Exactly. The phase angle phi is 90 degrees. This is the 0 power case we started with. Current flows, but no net energy is dissipated. This is what we call wattless current. Hope everything is clear so far. This concept explainer is from ProfSam.com. That is ProfSamt.tom.com. Let's quickly apply this with a simple example. Imagine a factory machine running off a 200-volt RMS source. The current measured is 5 amps RMS. Because of the motor's heavy windings, the circuit is very inductive, and the phase angle phi is 60 degrees. First, what is the power factor?
Cos of 60 degrees, that's 0.5.
Yes, 0.5. So only half the electrical effort is going into useful work. Now the total electrical effort, the apparent power S, is just V times I.
So 200 times 5, which is 1,000 VA.
1,000 VA. But the real power consumed, the useful liquid beer power, is P equals S times cos phi.
So that would be 1,000 times 0.5, which is just 500 watts.
Correct. The utility must supply capacity for 1,000 VA, but only 500 watts is being used. The other 500 VAR is just foam sloshing back and forth. Now let's connect this to our next topic, transformers. Why are those big distribution transformers you see on electricity poles always rated in kVA, kilovolt amperes, and not in kW kilowatts?
I think, based on the beer analogy, it must be because the transformer has to be built to handle the entire mug size.
Yeah.
It has to cope with the liquid in the phone.
You've got it. That's the perfect summary. A transformer is basically a set of copper windings. Its physical capacity, how hot it gets, how much current it can safely carry, is limited by the I squared R heat loss in its own windings. And that heat loss depends only on the total current I flowing through it. It doesn't care if the current is useful or not.
So the apparent power, V times I, is a direct measure of the stress on the transformer.
Exactly. It has to be strong enough to carry the total current or it will fail. That's why kVA is the standard rating. Okay, now for the silent killers. The subtle traps in the exam that look correct but will kill your marks. We have two major misconceptions here. The first, and most common, is confusing power factor with efficiency. Students often think if a motor has a power factor of 0.8, it means it's 80% efficient. That is wrong.
But why the confusion? They both sound like they measure how good a device is.
They do, but they measure completely different kinds of loss. Efficiency measures internal losses inside the machine friction, air resistance, heat loss in the machine's own wiring. Power factor, on the other hand, measures losses due to phase mismatch, which causes external I²R heating loss in the power lines outside the machine. The correction you must remember is this. A motor can be 100% efficient, no friction at all, but still have a low power factor because its windings are inductive. Remember this hook. Efficiency is friction loss. Power factor is phase mismatch.
Okay, that makes it very clear. An inefficient device wastes energy inside itself, but a low power factor device makes the entire power grid waste energy externally.
Precisely. Now for the second killer misconception, students hear wattless current, and they assume it means zero current flows. Again, wrong. In a purely capacitive or inductive circuit, the power factor is 0, but the impedancy can be quite small. So the current, I equals V by Z, can be absolutely massive.
That's so confusing. If a huge current is flowing, why do we call it wattless? It sounds like a contradiction.
It's called wattless because it transports zero net energy over a cycle. It's reactive. It borrows energy from the source in one quarter cycle and returns it perfectly in the next. The net work done is 0.
So it's not currentless, it's networkless.
Exactly. The crucial correction is that even though the current is wattless, that very high current still runs through the physical wires. And it causes very real, very costly I²R heating loss in those external lines. To remember this, think of this little story. Wattless current is like a busy bank teller moving lots of cash in and out of the vault all day, but ending with 0 net profit. Lots of movement, no gain, but the teller still gets tired and heats up the room. Okay, to make sure all of this stays locked in for your exams, let's use a few memory anchors. For the main formula, remember this mnemonic, PVIC. It stands for P equals V times I times cos phi. Power is VIC. Simple. For analyzing problems, always ask yourself this phrase, cos phi is the real deal. This reminds you that it's the cosine term that gives you the real power in watts, not the sine term, which is the reactive foam. And finally, a physical gesture. Hold your hand out straight. That's the current OI. Now, push forward directly with your finger. That is maximum work done. Phi is 0. Power factor is 1. Now, tilt your finger 90 degrees and push sideways. No forward work is done. That is PF equals 0. The angle you tilt is the phase angle, phi. Let's summarize the 3 main takeaways from this deep dive. 1. Average power in an AC circuit is P equals V I cos phi. The power factor, cos of phi, measures the effectiveness of power transfer, and it's always between 0 and 1. 2. The power factor is mathematically defined by the components as the ratio of resistance to impedance. Cos phi equals R by Z. Maximum power happens when the circuit is in resonance, making Z equal to R and cos phi equal to 1. And 3. Purely inductive or capacitive circuits have cos phi equal to 0. They consume 0 average power, and the current flowing is called wattless current, which contributes to transmission line losses, but not to useful work. And as a final thought, think about this. Many engineers say the greatest single energy efficiency gain in modern history didn't come from a new invention. It came from simply mastering the phase angle. Power factor correction, getting rid of that costly foam, is the invisible physics that truly powers our entire modern world. To get maximum marks in 12th CBSE physics, chemistry, and maths, visit ProfSam.com.
That is ProfSam, right?
Yes. ProfSam.com. Thank you for joining us for this deep dive. Study hard.